Problem 33, we're going to derive a trigonometric identity as a application of De Moivre's formula. So with n equals 2, De Moivre's formula tells us that cosine theta plus I sine theta squared is the same as cosine 2 theta plus I sine 2 theta. But on the other hand, we can square the left-hand side. And when we square the left-hand side, we're going to get cosine squared plus 2I cosine sine plus I sine squared. And that's again equals to the right-hand side. I'm not going to write it again though. Now, I squared, this is going to become a -1 when we square it, and then we're going to get a sine squared. So we have a cosine squared and a negative sine squared. I'm going to put parentheses just to associate them. And then the imaginary term is going to be, again, I'm going to put parentheses just to associate them. 2 sine cosine. And that needs to be equal to cosine 2 theta plus I sine 2 theta. Now, when two complex numbers are equal to each other, it must be that the real parts are equal and the imaginary parts are equal. So if we set the real parts equal to each other, we learn the following. We learn that cosine of 2 theta has to be equal to cosine squared minus sine squared. And we learn that sine of 2 theta has to be 2 sine cosine. Now, of course, we also have the Pythagorean identity in a thought bubble over here. That tells us that cosine squared plus sine squared is 1. And so in particular, by substituting appropriately, we'll get stuff like 1 minus 2 sine squared, or we'll get stuff like 2 cosine squared minus 1 as alternate double angle type formulas for cosine. But here, as a byproduct of De Moivre's formula, we have derived the double angle formula for sine and for cosine. And when you play with it for higher n values, you get triple, quadruple, and so forth angle formulas for these trig functions.